Hello there. In this video we're going to discuss more properties of exponential functions. In the last video we discussed functions of the form f of x is equal to a to the power of x, where a is a constant greater than 1. So we discussed that this graph will have some graph of the form this, where y is equal to 0 or is a horizontal asymptote, and this curve crosses the y-axis at the point 0, 1. So we're going to be focusing on two primary things in this video. We're going to be focusing on the transformations of this basic elementary curve, and we're also going to be looking at a special base of exponential functions known as e, and one of the limits or functions that this constant is related to. Alright, so let's start off with some transformations of exponential functions. Now, you should already be familiar with the transformations of basic algebraic functions such as quadratics, square roots, absolute values, and so on, so this property is going to be used here in the same exact way. So the first example that I'm going to look at is going to be g of x is equal to negative 4 multiplied by 2 to the power of x. So 2 to the x is going to serve as our elementary curve, where this graph has this type of structure. Now the only difference is this constant here, so we have a negative sign and this multiplying factor that's going to speed up the function in some regions of this curve. So this minus sign is the primary thing that we're going to look at, and then we're going to look at the stretch right after. So since that negative is going to flip it upside down, that means this graph is going to have this type of structure. Remember, this curve has a horizontal asymptote at y is equal to 0. This curve also is going to have the same exact thing because we're not shifting it up or down. Now, I just want to include one more piece of detail, namely the y-intercept. Now, this used to be at 0, 1. This is not 0, negative 1 because of this multiplying factor of 4. So I'm just going to plug in 0 into this function just to be sure or what this actually comes out to be. So this is going to be negative 4 times to the power of 0, which is going to be negative 4 times 1, which is going to be negative 4. So that means this point right here is 0, negative 4. Let's look at another. Let's look at h of x is equal to 7 to the power of x minus 2. So do you remember what this minus 2 does for the principal graph? So you should have said shift down. So this is going to be down 2. Since we're shifting the principal curve down, that means our horizontal asymptote is also going to shift down 2 units. So instead of being at y is equal to 0, it's going to shift down to y is equal to negative 2. So let's begin by drawing that piece of information. So our horizontal asymptote is going to be there. And let's also figure out where the the y-intercept is going to be. So h of 0 is going to be equal to 7 to the power of 0 minus 2, which is going to be 1 minus 2, which is going to be minus 1. So shifting all the points down with respect to this point, we're going to have that this is the graph of h. Let's look at another graph. So example 3. Suppose I have j of x is equal to 3 to the power of x minus 5. Now, what does it mean when I apply a transformation directly to the independent variable? So you should remember that this is a horizontal shift, namely to the right 5 units. So if I shift the horizontal asymptote to the left or right, the horizontal asymptote does not change. Only vertical asymptotes would change if I move it to the left or right, but exponential functions do not have vertical asymptotes. So now I'm going to take my point here, and I'm going to shift him over 2 units. So my curve should go over here. More in particular, that should be 5 units, right? Right. So that should be my graph, but it doesn't really look that much different, does it? Let's look into this a little bit more in detail. So I'm going to decompose this function into another form. So I'm going to rewrite this as 3 to the power of x divided by 3 to the power of 5 using our properties of exponents, which is just another way of writing 1 divided by 3 to the power of 5 times 3 to the power of x. So horizontal transformations to exponential functions actually can just be rewritten in terms of just stretching and shrinking of the principal graph, where we're pretty much compressing this value. So notice that if I plug in 0 into this curve, so j of 0 is just going to be equal to 1 to the 3/5, because that is the initial value of the exponential function, right? So if I go ahead and sketch this graph, so this is my basic exponential curve, and this point is going to be equal to 0 comma 1 over 3/5. Again, this is going to be x, j of x, and this black curve is going to be j. Let's take another example. So example 4. So I have k of x is going to be equal to 4 to the power of x plus 4. Again, horizontal transformations do not really change that much with respect to the overall structure of the graph. So I'm going to decompose this in terms of properties of exponents. So this is going to be 4 to the x times 4 to the 4th by our properties of exponents. So in our traditional way for exponential functions, this is just going to be equal to 4 to the 4th times 4 to the power of x. So if I were to go ahead and sketch the graph, so I have a horizontal asymptote, I have my exponential growth curve, because it's just 4 to the x, and then I have my y-intercept value, 0 comma 4 to the 4th. So this value is really large, so this is pretty much zoomed out from a normal 10 by 10 grid that we're used to looking at. And let's look at one more example, example 5. Suppose we have L of x is equal to 7 to the power of negative x plus 5. So first off, I have an exponential function with a negative growth term. So that means this is an example of exponential decay. It's an exponential decay curve, which typically has a horizontal asymptote of 0, that is shifted up 5 units. So instead of having a horizontal asymptote at 0, it's going to have a horizontal asymptote at 5. So I'm going to take my curve, I'm going to actually move my x-axis down a little bit. So I'm going to have a horizontal asymptote of 5. 1, 2, 3, 4, 5. There we go. And I'm going to have an exponential decay above. Right? So if I plug in 0 here, so L of 0, that's going to be equal to 7 to the minus 0 plus 5, which is going to be 1 plus 5, which is going to be 6. So that means this point right here, of course this is not drawn to scale, is going to be 0, comma 6, and it's going to be an exponential decay curve because of that minus sign. And that's the graph of L. Now, the next function that I'm going to introduce is a little bit more different than just the standard exponential functions. We're going to look at a composition of two functions, one being exponential and the other being rational. So I'm going to define f of y to be equal to y to the power of x, where x is going to be some real number with respect to f, and g of x is going to be a rational function, 1 plus 1 over x. So remember, if you recall rational functions, this is just the star graph shifted up 1 unit. And y to the x is almost like a polynomial, but x could be a real number, so it could be like x to the 1/2, x to the 1/3, or so on. So here's a question. So what is f composed with g of x equal to? So this is going to be f of g of x, which is going to be equal to f of 1 plus 1 over x. So I'm going to plug 1 plus 1 over x into the parameter of the function f. So that's going to be equal to 1 plus 1 over x to the power of x. So I'm going to define phi of x to be equal to 1 plus 1 over x to the power of x. Alright, so what is so special about this function? Well, I'm going to tell you this piece by piece and also show you a few applications in upcoming videos. So let's just evaluate this at a couple points to sort of get an idea of what this graph will look like. So phi of 1 is going to be equal to 1 plus 1 over 1 to the power of 1, which is the same as 2 plus 1, which is going to be equal to 2. So we have 1 point on the curve already. Let's plug in some fractions, such as 1/2. So this is going to be equal to 1 plus 1 over 1/2 to the power of 1/2, which is the same as the square root of 1 plus 2, which is the same as the square root of 3. So I can plug in, say, 1/10. That's going to be equal to 1 plus 1 over 1/10 to the power of 1/10, which is going to be equal to the 10th root of 1 plus 10, which is going to be equal to the 10th root of 11. So you should be able to verify by just looking at this pattern that phi of 1 over k is going to be equal to 1 plus 1 over k to the power of 1 over k, which is just going to be equal to the kth root of k plus 1. So now what I'm going to do is I'm going to send k to infinity. So as k goes to infinity, we know 1 over k is going to get close to 0 by properties of rational functions. So what happens as I approach 0 from the right-hand side, because we're approaching this with positive numbers? All right. So what happens to this function phi? So I'm going to just plug in a couple numbers here, or just analyze this just a bit. So this number here, so k plus 1, this number is going to get large. In particular, it's going to get positively large, right? So if that is getting positively large, what about the exponent? Well, the exponent, remember, k plus 1 to the power of 1 over k, this number here is getting really close to 0. So getting close to 0. So this expression is getting close to a positive number raised to the 0 power, which we know is going to be approximately close to 1 the closer you get to it. So that means as you approach 0 from the right-hand side, this function is going to get close to 1. So let's just sketch that out of what we know so far. So we know that when x is equal to, what was it, 1, I think? Yeah, 1. We got 2, right? And as x gets close to 0 from the right-hand side, it's going to get close to 1 but not touch it. So this is the graph of the function on the interval 0, 1. So now I want to look at this interval, namely when x is bigger than 1. So I can just plug in some numbers to get an idea of what this curve is doing. So f of 10 is going to be approximately equal to, and you can use a calculator to verify this, it's going to be close to 2.5937. If you plug in 100, you're going to get this is approximately equal to 2.7048. And if you plug in, say, 10,000, you're going to see this is approximately equal to 2.718148 or 9 or something like that. All right. So as you see, these numbers are increasing, right? So here's a little exercise for you to verify that f is increasing on the interval 1 to infinity, right? So I'll leave you that as a proof. Either you can use calculus if you know it, or just basic principles of functions and increasing behaviors if you want to know that. Also, another exercise I leave to the reader is that 5x is going to be always less than 3 for all x sufficiently greater than 0. So that means, okay, so the function is always increasing and the function is always less than 3. So this is another way of saying that the function is bounded above. So there's a property in real analysis, and you can prove this on your own, that if these two things are true, then that means as x goes to infinity, 5x is going to get close to some c that is less than 3. So some number it's going to get close to. And you can look at these decimal values and be like, okay, it's definitely getting close to something like 2.71 something, right? So we can define this number as e. There are other numbers or another way to define e, but we're going to introduce them in calculus. So we're just going to define it in this way, that as x approaches positive infinity, so as x gets really, really big, this number gets close to some number e, which is approximately equal to 2.718281 and so on. So that means the horizontal asymptote for phi is y is equal to e, where e is just some number defined as follows. Alright, so using this definition of e, what I want to do now is just do an example to show you how to find a horizontal asymptote of a function that isn't quite in this structure but has a similar feel to it, and how to find the horizontal asymptote of it using some basic algebraic transformations, right? So the function that I'm going to be considering is f of x is equal to 1 minus 2 divided by x to the power of x. Oh, and also to mention, one can show that as x gets close to negative infinity, that this function also still gets close to e. So as x goes to plus or minus infinity, so if you plug in really, really large negative numbers, you're still going to be getting close to this number, so that's important. Alright, so how can I get this in the same exact structure? So x is the independent variable for this, and I want this sign to be a plus and I want this thing to be a 1. So what I'm going to do is I'm going to reciprocate the negative 2 and I'm going to make it a negative 1/2 on the bottom. So I'm going to rewrite f of x to be equal to 1 plus 1 over negative 1/2 x to the power of x. Now remember, our original curve was 1 plus 1 over something to that something power. And we have negative 1/2 to the power of x, and maybe I need to introduce a negative 1/2 here. But the only way I can do that is if I raise this to a power of minus 2 so that those two things cancel out and we're not changing the actual function. So what I have here is f of x is equal to 1 plus 1 over negative 1/2 x to the power negative 1/2 x, all to the power of negative 2. And this is my function, right? In particular, this is phi of u, where u is equal to negative 1/2 x. And phi is that function that I defined before, right? So remember, one property of phi is that as u goes to plus or minus infinity, this function is going to get close to e, right? So what happens as u gets close to infinity with respect to x? Let's look at that in a little bit more detail. So as x gets close to positive infinity, u, which is equal to negative 1/2 x, is going to get close to what? So x is going to be really, really large, positive, multiplied by a negative number, so that's going to get close to minus infinity. And as x gets close to minus infinity, u, which again is going to equal to negative 1/2 x, so x is really, really negative times a negative number, so it's going to get close to a positive number. So in either case, as x gets close to infinity, u is going to get close to positive or negative infinity as well, right? So that means what? So that means the horizontal asymptote for our curve, right, which is the limit as x goes to infinity of, what was it? 1 plus 1 over negative 1/2 x to the power of negative 1/2 x to the power of negative 2 is going to be equal to the horizontal asymptote as u goes to plus or minus infinity of 1 plus 1 over u to the power of u raised to the power of minus 2. As we already know, this expression is going to get closer and closer to e, so that means this expression is going to get closer and closer to e to the minus 1/2, which is 1 over e squared. So that means what? That means the horizontal asymptote for y is equal to 1, actually I shouldn't use y, I should use f of x. So f of x is equal to 1 minus 2 over x to the power of x is going to be equal to, y is equal to 1 over e squared, right? So I leave you as an exercise to prove the following, that the horizontal asymptote of 1 plus a over x to the power of x is y is equal to e to the power of a. So you can follow the same exact protocol if you want to. So that's just some more advanced properties of exponential functions and how they sort of interact with rational functions. Hope you enjoyed.